Good day. Welcome to our group's project, Offshore Petroleum Operations and its Environmental Impact. Our group members are Sanjeev Maraj, Justin Sinat, and myself, Art Cupid. So we want to start by talking about marine uses for offshore. There are many uses for marine offshore. These marine uses results in physical presence and physical disturbances. Next slide. So some of these marine uses for offshore include surveying, drilling, construction, production, and decommissioning. All right, so these uses, they result in physical presence and physical disturbances. Physical presence, where physical objects associated with offshore projects consists of a range of surface and subsurface structures and vessels. Surface structures may include drilling units, semi-subs and jackups, drill ships, fixed platforms, FPSO vessels, floating storage and regasification units, and floating liquefied natural gas facilities. Subsea infrastructure may include pipelines, risers, flow lines, umbilicals, manifolds, and Christmas trees. And vessels, project-related vessels, may include survey vessels, seismic, geotechnical, barges, tugs, support heavy lift and anchor handling vessels, and intervention vessels, and trenching and pipe laying vessels. So the impact of physical presence, right? Permanent presence of facilities or infrastructure, right? Impacts may occur from the permanent presence of facilities, infrastructure over the life of a development and during removal of infrastructure during commissioning. Placement of these facilities and infrastructure. This may require anchoring to the seabed or in the case of a fixed structure, such as a platform, installation of foundations, either of which would result in the temporary or permanent loss of habitat. Vessels traffic. Vessels traffic may be present throughout a project and may include a range of movements to and from a sea project area. The increase in vessel traffic may increase the risk of collision and obstruction to others. The potential environmental impacts and risks associated with the physical presence of vessels and equipment include increased suspended sediments and sedimentation, disturbance to or loss of benthic seafloor habitat and associated biota, creation of artificial habitat and or modification of existing habitats, introduction of marine invasive species, disturbance to the marine archaeology, disturbance to migration, feeding, and breeding patterns of areas, and deviations to migration pathway, visual aesthetics, impacts to seascape resulting in social and cultural impacts, vessel interaction with marine fauna, example vessel strikes, and interaction with other marine users that may lead to potential displacement. So mitigation management measures, right? Mitigation management measures and performance standards applicable to the management of physical presence include considering sensitive marine habitats and life cycle periods for relevant species and communities during the site selection and design stages. Undertake benthic habitat surveys to identify sensitive habitats and biota, and where feasible, avoid these areas, and to minimize physical footprint where feasible. Consider potential impacts for offshore structures. At an early stage, consider potential impacts for offshore structures, both positive and negative. In some cases, restoration may be needed to assist the recovery of damaged or destroyed habitat or offset considered. Examples are the introduction of artificial or transported habitats, reefs, and the relocation of individual coral colonies. Dynamic positioning. Consider dynamic positioning on drill rigs to avoid or minimize the need for anchors. Develop exclusion zones in consulting with key stakeholders, including local fishing communities. Raise awareness of exclusion zones with all stakeholders. Ensure all facilities or infrastructure has the appropriate navigation lighting, and all facilities, infrastructure, and subsea infrastructure is gazetted and included on navigational charts to avoid collision. Issue a notice to marinas through the relevant government agencies detailing the area of operations. Develop and implement collision risk management plans for vessels. Ensure all vessels adhere to international regulations for preventing collisions at sea, which set out the navigation rules to be followed to prevent collisions between two or more vessels. Optimize vessel use to ensure the number of vessels required and length of time that vessels are on site is as low as practicable. Physical disturbance, dredging, trenching, and mud dumping. Dredging and pipeline trenching involves the removal of sediments and debris, typically during the construction, installation, and commissioning phases of the project. Maintenance dredging can also be required over a project's life cycle, most likely in small quantities. The material collected during dredging is known as spoil and is usually disposed of offshore. Methods include grab dredging, backhoe dredging, trailing suction hopper dredgers, water injection dredgers, and seabed leveling. Dredging can occur in a diverse range of environments involving a range of sediments. In areas remote from pollution sources, sediments are unlikely to contain contaminants, while in ports and harbors adjacent to urbanized or industrial areas, sediments may contain high levels of contamination from metals, hydrocarbons, and synthetic organic compounds. Some marine environments are also more sensitive to dredging impacts and require a higher level of protection. For example, coral reefs and or fish nurseries. Next one. Dumping. What is dumping? Dumping is a method used to stabilize or protect pipelines, or may be used to stabilize locations for placement of jackup rigs. Next. Dredging, trenching, dumping, and the offshore disposal of dredge spoils creates turbid plumes, sand transport, coastal sedimentation, and underwater noise. Next. The potential environmental impacts and risks associated with physical disturbances includes habitat modification, removal, destruction of sensitive marine habitats, increase in suspended sediments, resulting in the burial of sessile flora and fauna and interfering with local prey and alternating the movement of larval fish. Increase in sedimentation or placement of materials, resulting in burial of sessile flora and fauna, alteration of the hydrodynamic processes, reduced productivity of fisheries, and noise impacts. So some mitigation methods include considering sensitive marine habitats and life cycle periods for relevant species when determining the placement and timing of dredging zones during the site selection and design stage. Reduce footprint. Reduce footprint duration and volume of dredging, rock dumping, and dredge disposal to the minimum required. Establish a dredge management plan that outlines measures to minimize impacts and suitable management responses when trigger values for marine water quality are exceeded. and develop plans for exclusion zones in consultation with key stakeholders, including local fishing communities, raise awareness of exclusion zones with all stakeholders, obtain permits for approved disposal routes. I'll now pass you over to Sanjeev, who will discuss emissions.
Okay, so emissions. Emissions such as acoustic emissions are emissions that are underwater noise and underwater vibrations. Right, so underwater noise in the oil and gas industry comes from exploration. This is where noise is generated from seismic survey and geophysical surveys. This creates high energy pulses of low frequency sound. Construction. This is the noise created due to piling, dredging, and trenching. Drilling and production. This is the noise generated due to ground vibration when setting up offshore rigs, such as semi-submersible rigs, jackup rigs, and drill ships. Drill ships make the most noise than platform rigs. Mechanical vibration is also created due to drilling underwater. Decommissioning. This is the noise created by vessel propulsion and positioning. Vessels and shipping. This is a noise that is generated by machinery on the vessel, such as generators, engines, pumps, etc. So, the environmental impact to marine fauna due to underwater noise are behavioral changes. These are the changes that include temporal changes in swim behavior or direction, season of vocalization, changes to breathing, and changes to migratory regimes. Auditory interference, masking or interfering with other biological important sounds such as communication, echolocation, and sounds produced by predators or prey. Auditory impairment, permanent or temporary impairment to hearing organs. Mitigations of acoustic emissions are consider sensitive locations and time of year when planning seismic activity. Utilize marine mammal observers for sensitive species in the area. Use passive acoustic monitoring in highly sensitive areas. Use soft start procedures for piling operations and dredging. For pile driving, consider the use of vibratory hammers and air bubble curtains. Assess whether anchoring or the use of dynamic positioning would be more appropriate for maintaining a ship's position. Consider engineering measures to minimize operational noise emissions. So now I'll go to combustion emissions. Combustion emissions occur from offshore activities such as electric power generation, machine drivers for compression and pumping, gas flaring, vessel activity, helicopters. Environmental impacts are due to carbon dioxide, which is a greenhouse gas that contributes to climate change and ocean acidification. Nitrogen oxides contribute to acid rain and may also contribute to ozone formation when mixed with volatile organic compounds in sunlight. Nitrous oxide is a greenhouse gas that contributes to climate change. Sulfur dioxide contributes to ocean acidification and acid rain. Carbon monoxide can be oxidized to carbon dioxide, but is primarily a local air pollutant that can be toxic at high concentrations. Methane is a greenhouse gas that contributes to climate change. It also contributes to low-level ozone formation. Volatile organic compounds, or VOCs, can promote the formation of photochemical oxidants and contribute to climate change. Mitigations for combustion emissions are the use of high efficiency equipment to minimize power demand, do life of field planning, select low sulfur diesel, power generation plants incorporating low emissions technology as a standard. Small combustion process installations should be designed to meet the emissions guidelines. Integration of renewable energy sources into developments. Consideration of electrification versus direct drive when designing projects. Do regular plant maintenance, and implement emissions control devices on vehicles and machinery. All right, so next I will go to fugitive emissions. Fugitive emissions include those emissions that are targeted by operating facilities as part of their leak detection and repair survey programs, with particular focus on valves, flanges, pumps, connectors, and compressors. All right, so the environmental impact is contributed to global warming, since most of the fugitive emissions are methane. Mitigations for fugitive emissions are selection of appropriate valves, flanges, fittings, seals, and packings, considering equipment safety and suitability requirements, as well as their capacity to reduce gas leaks and fugitive emissions, implementation of effective and regular leak detection and repair programs, ensuring new systems or processes do not use chlorofluorocarbons. Next, I will go on to venting. These are emissions from volatile organic compounds, or VOCs. The environmental impact would be emissions from venting, which contributes to global warming. So mitigations of venting are to adopt measures consistent with venting reduction voluntary standards, tightly controlled and managed flow of gas, preferentially flare rather than vent, vapor recovery units installed as needed for hydrocarbon loading and unloading operations, incorporate BAT for use of venting, including maintenance, ensure efficient running of equipment. In the event of emergency or equipment failure, excess gas should not be vented, but sent to an efficient flare gas system. Flaring. These are emissions from natural gas, such as carbon dioxide and other combustion emissions at the flare tip. Mitigations for flaring are to adopt measures consistent with global gas flaring standards, ensuring a tightly controlled and managed flow of gas, design of flare gas metering and tip design to minimize the need for flaring through recirculation of gas recovery and or flare gas recovery process design. Careful flow tip design, implementing best available technology, reducing the amount of air pollutants, maximize flare combustion efficiency by controlling and optimizing flare fuel, air, and stream flow rates to ensure the correct ratio of assist stream to flare stream. Minimize flaring from purges and pilots. Minimize risk of pilot blowout by ensuring sufficient exit velocity and providing wind guards. In the event of an emergency or equipment failure, excess gas should not be flared, but sent to an efficient flare gas system. I will now pass you on to Justin Sinat, who will discuss offshore discharges, sorry.
Hi, good day. I'll be doing offshore discharge, so let's get to it one time.
Okay.
Next slide. So we have sewage, grey water, and food waste. So this can be found in showers, toilets, and kitchen facilities, right? So the effects on the environment can be changes in changes to ambient water quality. This can increase the BOD, which is the biological oxygen demand, biostimulation of planktonic communities, biological exposures to pathogens, which can also decrease water quality and decrease sediment quality due to the sediments and solid food waste. So the mitigation, water should be treated according to the MARPOL Annex 5. Next slide. And the sediments in the food waste especially should be less than 2.5 millimeter before discharging into marine environment. Deck drainage and bilge water. So deck drainage and bilge water, this is like surface runoff, as in like if we wash off a platform, what drainage water from equipment, surface, etc. So the impacts on this to the environment: change in ambient water quality due to oil residue on platforms and equipment, and due to the chemicals in the equipment, toxicity can increase. So management required for this system: vessels must have a valid international oil pollution prevention certificate. Hydrocarbons and chemical storage areas should be bounded with no residues, no spills, oil record books, but this is only necessary for vessels of 400 gross tonnage and above. Suitable containers for oil dispensing and hazardous waste. Fluorine-free firefighting is also recommended because fluorine can persist in the environment and cause bioaccumulations. Next. Coolant water and desalination brine, right? So coolant water is, there's an intake that is pulled from the sea, cools the system, and is dispensed out into the sea. Desalination is a process by taking salt water and purifying into fresh potable water. Next. Due to the coolant water, high temperatures occur since heat is absorbed into the water before dispensing into the environment. Chemical effects occurs due to water being in contact with chemicals on the platform and during the cooling process. High salinity from desalination occurs after the process is done. Also, high salts and high concentrations in salts also occurs due to desalination. Management. So we have rapid dispersion designs. So when designing systems, we want to make sure that when released into the environment, that it is dispensed and dispersed into the sea quickly to not cause accumulation into the sea. So we want to minimize biocide dosing and limited freshwater. Now this means we don't want to use water that we don't need, so just have the desalination plants running to purify water that is needed on the platform. Next. Hydrotesting. So hydrotesting is undertaken by filling different infrastructure components with hydrotest water that consists of filtered, inhibited seawater containing chemicals. So this is done to mimic a subsea surface and test the pipelines before it is actually run and put to use. So chemicals may include monoethylene glycol, triethylene glycol, biocides, corrosion inhibitor, scale inhibitor, dye, and oxygen, etc. So effects of hydrotesting in the environment: we have a decline in DO, which is dissolved oxygen, because hydrotest uses the oxygen. Therefore, when dispensed into the environment, release lower oxygen in the marine. So we have a higher toxicity due to the chemicals used in hydrotesting. So solutions: hydrotest onshore. So we would like to hydrotest onshore rather than offshore. Reduce chemicals, only use chemicals that is needed for that project and make sure it is environmental friendly. Onshore treatment and disposal. If necessary and where applicable, we can send waste to this, we can store waste and send onshore for treatment and disposal. Next. Produced water. So produced water, also known as formation water, refers to the water that occurs naturally in hydrocarbons when it is being produced. So the composition of produced water is dissolved salts, trace concentrations of metals, suspended particles, suspended and dissolved hydrocarbons, fatty acids, and other organic compounds. Chemicals are also added in produced water, not added. Chemicals are also found in produced water. So how is it discharged? So we can store produced water and send offshore again here, or we can re-inject into the well to help with production or treatment and disposal to marine environment. This is sometimes we can treat offshore and dispose in the marine environment. Next. Impact on the environment, reduce water quality due to the chemicals, and this chemical can also increase toxicity, thus affecting flora and fauna. Now, the water temperature will increase due to geothermal temperatures in the well, which was a high temperature, thus causing the temperature of the water increase and causing a hotter temperature, generally about 20, no, not 20 degrees, generally hotter temperature to be in the environment. Next. So as we said earlier, we can recycle by re-injection into the well, disposal techniques. So we have different disposal techniques and it must meet guidelines for disposal. So we have the World Bank EHS guideline for offshore oil and gas development, or the EU hydrocarbons BAT guidelines, either or, whichever is necessary at that process. So we want to maximize dispersion here again, and designing chemicals must be selected carefully. So we want to use chemicals that is environmental friendly, and so that they will not alter the flora and fauna in the environment. Next. Right. Ballast water. So these ballast water are used for stability in drill ships during, as we can see, drilling. So IMS occurs. IMS is introduced marine species. So this is when ships taking water, species can be taken in. Now, when this happens, a ship can take in water at point A and release at point B, thus releasing species from point A in point B. To manage this, we have vessel compliant to guidelines. So we ensure vessels compliance with local regulatory authority guidelines, and all ships have to manage their ballast water and sediments in tanks. So this will help to minimize the IMS occurring. Next. So produce sand and scale. Sand is produced from the reservoir when separated from a formation fluid during hydrocarbon processing. So we can get NORMS. NORMS is a contamination and it is radioactive and we don't want it. So this can include uranium, thorium, potassium, radium, and radon. So as we know, anything radioactive is very devastating to the environment. So we don't want this in the environment. But if, however, it gets into the environment, these are some of the effects. So we have subsea disturbance, toxicity increases due to the radioactivity, reduced water and sediment quality. Because of the sand, it can have oil residue, thus increasing the oil and grease content of the water. Next. So management. So we want to try our best to transport this waste to the shore to be disposed. Under no circumstances we want to make this discharging into the sea regular, because this can greatly affect the flora and fauna. And discharge should meet, again, the guidelines of World Bank's EHS guidelines for offshore and oil and gas 2015, or EU hydrocarbon BAT guidance. Next. Drill and discharge. So we have 3 types of discharges in drilling. We have drilling cuttings, drilling muds, and cements. Right, next. So we have the environmental impacts. Here we have drilling muds and cement especially can increase the turbidity of the water. Now, increasing turbidity decreases the light penetration, thus changing the flora and fauna below the subsurface. So we have, because of the turbidity increase and light decreasing, turbidity increase and light decreases, it smothers the benthic community, therefore altering the sediment. So cement in particular will sink to the bottom and cause sediments to be altered and change. Toxicity increases due to the chemical impacts of oil-based muds, if that's what was used. Cement also has a lot of chemicals that can increase toxicity. And decline in sediment quality due to settling and cement being around the area. Next. So management measures here, we can have calculated amounts of drilling, cuttings, and fluids. So we want to store cuttings to be disposed of either onshore or separated out offshore. And fluids, so we want to have a calculated amount of fluids, so we will not have a lot being wasted and dispensed out into the sea. Same as with the cement, we want to have a calculated amount, and we want to select the appropriate drilling fluid. So we don't want to use an oil-based fluid when we could use a water-based fluid. So we want it to be most environmentally friendly as possible. So we have recover and store oil-based mud. So after using oil-based mud, we don't want to dispense this into the sea just yet. We have to put this through a system of separating out the oil, and then we can discharge only if necessary. So solid control techniques, we have equipment on board to drill that can break up the sediment into smaller and minimize the sediment before it is dispersed into the sea. Only if necessary, we want to dispense this oil-based mud into the sea. That's what I'm gonna say one more thing. The oil-based mud is dispensed only if necessary and if the dispersion is high, so that sedimenting will not occur. I'll now hand you back over to Art, where he will continue waste.
Different types of processes that causes offshore waste. We have processes and production chemicals. A variety of chemicals may be used during the processing and production, such as subsea control fluids and completion fluids and well workover fluids. Production. During production, chemicals such as subsea control fluids are used to control subsea valves remotely from the facility. Subsea control fluids are typically water-based with additives of MEG, which is a monoethylene glycol. It is widely used as a hydrate inhibitor in the oil and gas industry to reduce the risk of hydrates forming in pipelines that could cause blockage. For flow assurance and hydrate inhibitor purposes, large volumes of MEG are required to control the hydrate formation condition in pipelines, lubricants, corrosion inhibitors, biocides, and surfactants. Subsea control systems can be either open or closed loop systems. Where open loop systems are employed, typically small volumes of fluid are discharged to the marine environment intermittently. Where closed loop systems are employed, fluid discharges to the marine environment do not occur under normal operating conditions. The emissions of these chemicals to the marine Given the low volumes typically released, the emissions of these chemicals to the marine environment may result in a localized change to the water quality and toxicity to marine biota. Completion and well workover fluids are used to clean the wellbore and stimulate the flow of hydrocarbons, or may be used to maintain downward pressure. They include intervention fluids and service fluids and typically comprise of solid material, residual drilling fluids, weighted brines or acids, hydrocarbons, MEG, and other types of performance-enhancing additives. So some mitigation measures used. Selection of control fluid. You want to select a water-soluble, low-toxicity control fluid. Selection of chemicals based on OSPA and HMCS. Selection of chemicals to be used and discharged offshore based on the Oil Spill Prevention Administration and Response, OSPA, or Harmonized Mandatory Control System, HMCS. If using a closed system, collect the fluids were handled in closed systems and shipped to shore for recycling or treatment and or disposal. Injection and a disposal well were available. If discharging to the sea, select chemical systems in relation to their concentration, toxicity, bioavailability, bioaccumulation potential, with a preference to ONCS, which is Offshore Chemical Notification Scheme, Group E, or PLONO, pose little or no risk to the environment chemicals. Consider routing fluids to the proposed water stream for disposal or reinjection if available. Neutralize spent acids before treatment and disposal. Ensure fluids meet the discharge levels for the different governing bodies, and design of equipment to reduce volume of fluid release. Hazardous waste. What is hazardous waste? Hazardous waste is any waste that, if not handled, stored, or disposed of in an appropriate manner, presents a significant risk to health, safety, and the environment. Hazardous wastes are normally disposed of in an appropriate manner, which would only enter the marine environment in the event of an accident, loss, or spill. Hazardous waste generated during all phases of a project may include, but are not limited to, recovered solvents, excess or spent chemicals, paint, biological waste from medical facilities, oil-contaminated materials, batteries, fluorescent light tubes, waste oil, mercury removal absorbents, contaminated containers used for storage of hazardous material. Next slide. Next slide. Impacts of hazardous waste. The level of impact from a discharge is dependent on the nature, volume, and location of spill release, as well as its behavior in the marine environment. Example, settlement to the seabed or rapid dispersion. The potential environmental impacts associated with the accidental discharge of hazardous waste includes temporary and localized reduction in water quality and resulting toxicity effects to marine flora and fauna. Settlement of non-buoyant material on the seabed, resulting in direct localized impacts to benthic habitats and localized alteration of geomorphical seabed features. Release of buoyant material potentially impacting marine fauna due to entanglement, ingestion, and smothering. So some mitigation measures include segregation of hazards, segregate hazardous waste in hazardous waste skips and drums or holding tanks for liquid waste prior to disposal. Hazardous waste to be managed and handled and stored in accordance with their SDS, their safety data sheet, and tracked from source to their final destination at an appropriately licensed waste facilities. So non-hazardous solid waste. General non-hazardous solid waste are generated through all phases of the oil and gas life cycle through normal operations. Types of non-hazardous waste include paper, rope, cupboard, sacking, timber, scrap metal, domestic packaging, food and drink containers, etc., and plastic. How does it enter the sea? It enters the sea from inadequate storage or disposal procedures. So inadequate storage and disposal procedures results in environmental impact from the accidental loss of waste into the ocean. Example, wind blowing lighter materials such as paper or plastic into the ocean. The effects of accidental discharges of solid waste, these are dependent on the nature of the material involved. The potential impacts associated with solid waste are ingestion of solid waste, ingestion of objects, including waste by marine fauna and avifauna, potentially leading to injury or death. Entanglement of marine fauna in plastic or other solid waste, potentially leading to injury or death. Smothering of benthic habitats. Physical contact and potential smothering of benthic habitats, which relates to the habitats at the bottom of a body of water. Potential water quality deterioration. Potential water quality deterioration within the direct vicinity of the source resulted in behavioral changes in the marine species. So some mitigation methods include non-hazardous solid waste to be managed in accordance with MAPOL 73.7 Annex 5 requirements, which states that harmful substances shall be properly stored and secured so as to minimize the hazards to the marine environment without impairing the safety of the ship and persons on board. Disposal of solid waste. No planned offshore disposal of solid waste should be employed. And waste segregation. Waste are to be segregated at source into recyclable and non-recyclable waste, where net environmental benefit is likely, and stored in marked containers for transport onshore to a recycling contractor wherever practicable, or a waste disposal site if available. I now pass you over to Sanjeev to talk about unplanned events.
So in unplanned events, we have accidental release, bulk chemicals. So accident release of bulk chemicals to marine environment are water-based muds, methanol, MEG, hydraulic fluids, paint thinners, waste oil, cleaning agents. Potential impacts of chemical spills to marine environment are temporary localized decline in water quality, temporary localized decline in sediment quality, temporary minor toxicity to marine flora and fauna. Mitigations for chemical spills include vessels must have valid international oil pollution prevention certificate, must have a shipboard marine pollution emergency plan, comply with stowage requirements for vessels, drilling units carrying harmful substances in package form. Chemicals should be stored in secure designated areas with secondary containment. SDS should be available on board for all hazardous substances. Chemical spills containment and recovery equipment should be available near chemical inventories. Chemical transfer should be undertaken in suitable weather conditions. Comply with facility or vessel lifting and drilling fluid procedures. All right. I'm going on now to spills due to vessel collision, tank, and pipeline rupture. So these spills are caused by vessel collision, tank, and pipeline rupture, and are due to navigational error, vessel loss of power, and foundering due to weather. So the potential marine impacts include potential deterioration in water quality and sediment quality, potential toxic effects to marine biota, physical oiling of marine megafauna and seabirds, social impacts to fisheries, disruption to other marine users from the presence of the slick, intertidal and shoreline impacts on human uses, flora and fauna. Mitigations. These vessel mitigations include implementing safety exclusion zone for relevant vessel or facilities, vessel-specific controls aligned with MARPOL 7378, which includes managing spills on board, emergency drills, waste management requirements, and having in place an SOPEP. Vessel movement comply with maritime standards such as Colgras and SOLAS. Select vessels that have isolated fuel tanks and have a double hull design. Have vessels with radar on board fitted with a collision alarm. Have vessels that can maintain appropriate lighting, shapes, navigation, and communication systems at all times. Pipeline mitigations include hydrotesting to be undertaken prior to commissioning to ensure there are no leaks in the pipeline. Pipelines to be stabilized and protected through trenching and burial and deployment of rock armor as necessary. Monitoring of subsea equipment to be undertaken, including through periodic intelligent pigging operations, monitoring of corrosion and corrosion protection system, periodic inspections using side scan sonar and remotely operated vehicles, implementation of ongoing maintenance and inspection procedures, simultaneous operation procedure to be implemented, and spill preparedness measures and emergency response procedures in place. So now I will go on to what is called spills that occurs due to refueling and bunkering. Right, so these are small hydrocarbon spills that occur during refueling operations. Potential impacts include potential reduction in water quality, potential toxic effects to marine fauna, localized avoidance of water by fishermen. Mitigations include conducting port refueling where practical. Refueling at sea must be conducted by trained personnel using defined procedures, conducting regular inspection of transfer hose integrity, continuously monitor tank levels to prevent overflow, dry bake or breakaway couplings to be used where available and practical. All vessels must include an SOPP and oil spill response measures. So now I will go on to major spills from exploration and production facilities. And this is due to loss of well control, which contributes to large oil spills. Actually, this is due to loss of well control, which contributes to large oil spills. Potential impacts include reduction in water and sediment quality, direct toxic or psychological effects on marine life, hydrocarbon contacts with banks, reefs, and islands at concentrations that result in adverse impacts, alteration of biological communities as a result of the effects on key marine biota, social impacts on marine archaeology, commercial fishing, traditional and subsistence fishing, tourism, recreation, scientific research, health, and commercial shipping. Mitigations include conducting well-designed and controlled activities with industry's best practice standards, oil spill modeling to be undertaken to determine the potential impact to the surrounding environment, blowout prevention measures to focus on maintaining wellbore hydrostatic pressure, conduct well integrity testing, implement a well operation management plan, implement a well control contingency plan, install a certified blowout preventer, implement well isolation barriers and well intervention procedures to be in place, have emergency and spill response measures in place, conduct ongoing maintenance and inspection procedures. I will now go on to collision with marine fauna. So the potential impacts are potential blocking of feeding areas and migration pathways, entanglement due to seismic vessel equipment. Mitigations include monitor for presence and movement of marine fauna, apply species-specific management actions to minimize adverse interactions, including no tangle gear attached to the streamers when using seismic equipment. Create plans for rescue and release of entangled animals, employing a MMO to monitor marine fauna. So I'll go on now to introduction to invasive marine species. These species are microorganisms, small invertebrates, eggs, cysts, larvae, or various species. Potential impacts include decline or extinction of species due to competing for space and food with native species, decline and extinction of species due to predation of native species, decline or extinction of species due to disease and pathogens. Right? Alteration of food web dynamics, changes in habitat structure, alterations of environmental conditions. So those are the potential impacts. The IMS mitigations include developing an IMS management plan, controlling harmful anti-fouling system on ships, ensuring vessels have an international anti-fouling system certificate, conducting regular inspections of the hull. And finally, we have ballast water mitigations, ensuring vessel compliance with local regulatory authority guidelines, manage ballast water according to ship specification ballast water management plan. All ships must have a ballast water record book. All ships must have an international ballast water management certificate. We have come to the end of our presentation. Thank you.